start the main last test that we will be doing in here. And here, let me guide you down the path as to what this test does for you. First thing is, when we reviewed the regressions on Friday, you know, the scatter plots and the lines and all that kind of stuff, I said, hey, get your correlation coefficient. And that was, what letter represented your correlation coefficient? Okay. And that gave us an indication of linearity. But then I said, oh, that might not be good enough. So what did I have you check next? Non-coefficient. The residual plot. Because if there was what? If there was a pattern in the residual plot, then that's bad. If there was no pattern in the residual plot, then what could we say? A linear model is appropriate. Okay. That is not the final frontier. The final frontier is this thing right here, which is the linear regression t-test, because in order to find statistical evidence, in order to find this thing, quote unquote, statistical evidence, you have to have a p-value. Alright, so therefore we have to run a test to see if linearity is statistically significant. Okay, so this test is going to be a test about slope. That is its main purpose, because what happens is we say, hey, you know what? If we've got a slope between two variables, then we've got something linear going on. If, and here would be your null hypothesis, if the slope of the population, which is represented by this capital beta, we've seen that before, it was type 2 error probability, but what would it look like for there to be no relationship going on? What type of slope would you have if you have no linear relationship? What do you think that slope would be? 0, that's right. So what we're going to end up seeing when we run our tests is that if we have a slope of 0 in the sample, then we have no linear relationship. But if we have a sample that has a slope far enough away from 0, then I will reject the null hypothesis, and then what will I conclude? Yeah, if I reject the null and I choose the alternative, then I have evidence that there is a linear relationship. A linear model is appropriate and that there is a linear relationship. Okay, so that's what we're headed down. I think I'm going to get, here, you ready? You want to have a little insight into my latest song? Okay, here, hold on a minute. All right, back to this. So, now that you have an idea of what we're headed for, correlation coefficient is not enough. Residual plot is not, quote unquote, proof. You have to have p-value to have statistical evidence, so we will run a linear regression t-test. So, here is our computer printout. And what I want to do with that is show you all this information. We already see that this is a relationship between volume and height of an item. Okay. They also give us the equation in this printout right here that volume is negative 87.1 plus 1.54 height. What is missing notationally from that statement? What's the notation missing from right there? The hat. Because this is a predicted volume. So remember that that is never given to us in a printout. Okay? All right. But in the event that that was not there, okay, in the event that we did not have that at all, then what are we going to do. So say we didn't have this. How are we going to get that equation of the line? No, because we don't have individual pieces of data given to us. Right here. These coefficients are where you get your equation. Which one of those is the slope? The bottom one is the slope, because this is the line all about slope. That's your x variable, so the coefficient with your x variable is the slope. All right. And so how would you interpret this slope, by the way? You would say, for every 1 unit increase in height, for every 1 unit increase in height, what's going to happen?
Volume increase.
The volume increases by about 1.5433 units, whatever that is. Okay. Now, look at this y-intercept. This is very interesting. This y-intercept is negative 87.12. What is of interest to you? Yeah, it's negative. That's a little disturbing because if you understand context, this y-intercept is happening when x is 0. Okay? So let's think about that for a second. I got this. Got this. Height is your x variable. Volume is your y variable. And we got this happening. Right here is negative 87 volume. So, does that seem plausible in the context of this problem that when your height is 0, your volume is, the volume of the item or whatever is negative 87 units? Is that plausible? No. Y-intercepts are frequently and most always, what? Inaccurate and not a true representation of this data. Why do you think that happens?
It's not perfect.
Aha! Because the data that we have might be linear right here. Okay? Maybe the information is appropriate to be linear right here in this area. But does that tell me what's happening outside of that area? Ah, very good. Yeah, just because this is appropriate to be linear does not mean it doesn't like take a whole different shape outside of the data. Here is the data, and it's appropriate to be linear right there. But outside of that data, I don't know. And in this case, well, in all cases, the definition of if you make a prediction outside of the data, then that is called an extrapolation. So that is what the y-intercept falls victim to very frequently. This is far outside the data, therefore it's considered extrapolation and it's not appropriate to make an estimate that far outside of the data. Okay, so that's why the y-intercepts are typically a poor indicator of we don't want to make any predictions there. And hence, this information here is rarely needed for this class at all because we never are really predicting the y-intercept. And so let's talk about what these items are. This first item here is the standard error of the coefficient. Standard error is like standard deviation. So it's the variability, like how much your slope or your y-intercept can go up and down. Because when I made this slope right here, is this definitely the slope of the population? No. I'm going to be off a little because how did I get this number right here? From a sample. I got this number from a sample. So I don't know that that is a fact. And I've got some variability happening right here. This is the variability in my slope. This is the standard deviation, also called standard error. It's called standard error when it's made from a sample and it's not the whole population standard deviation, okay? So it's standard error. It's basically how much you anticipate your slope could be off from what you got from your sample. So that's the standard deviation of the slope, or standard error of the slope. Okay, yes. Well, in a sense, we could make an interval. And in fact, let's think about what that means. Our predicted slope for this problem from the data, from the sample, was 1.543 whatever units, okay? Well, guess what? The standard deviation, the standard error for the slope is 0.3839. That's kind of an indication of the wiggle room that I allow myself that this might be off. Okay? So whenever we have a normal curve, because we're actually going to kind of be thinking of these in terms of normal, even though they are T models, they're nearly normal, okay? How many standard deviations is kind of like the threshold of what I'll allow myself to be variable to. Well, 3, crazy 3, but 2 is mostly what we talk about. 95% of the data should be contained within 2 standard deviations. So watch this. If I took my slope of 1.543 and I added 2 of these standard deviations, then this is kind of giving me an upper threshold for slope. So in a sense, yes, I'm almost kind of coming up with an interval, and this slope would be steeper, 0.3839 times 2 steeper, or whatever. Okay, this would be kind of like that final threshold on the upper end. But how about on the lower end? On the lower end, if I went 1.543 and I subtracted away 2 of those standard deviations, that will kind of give me a lower slope boundary. And so in a sense, I've kind of got, a less steep slope. So do you see, my slope could look like this. My slope could look like this, or it could be, steeper. It could be this steep. Now, where it's pinpointed, like where it's angling off of, I don't know. That'd be different y-intercepts and stuff. Okay, but I could have a steeper slope, less steep slope, but this is kind of a guideline of your threshold of changes that can happen. Okay, that is what this does for you. This is kind of indicates how much your slope could be off to be reasonable. If I was 2 whole points off, like the number 2, is that reasonable? If I was off, if I found that my estimate was 2.5 units off, or whatever, the slope was 2.5 off, would that be reasonable? Yeah, and that would be a whole bunch of these 0.3839s. 2.5 is a whole bunch of these 0.3839s. That would be a whole bunch of standard deviations off. All right, but that's we'll do physical representation of that more tomorrow. All right, now next, this right here is a t-distribution value. That is saying how far away your sample slope, which is this right here, 1.5433, is away from what was hypothesized. So guess what? This t is my sample slope, 1.543, minus the hypothesized slope. What's the hypothesized slope? Dun, 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 dun. What? 0, right here. Hypothesized slope, meaning no relationship, over, what do we put on the bottom of those things? Standard deviation. And what standard deviation am I going to put? Boom, this 0.3839. So if I do this, Guess what that t-value comes out to be? 1.543 minus 0 over 0.3839. Ta-da! 4.02. That's kind of how many of those slope standard deviations you were away from 0, which then gives us a p-value. P-value, statistical evidence. This is what we're going for. What is a p-value of basically 0 going to tell us? We should reject the null. The null is saying what? No linear relationship. So I am rejecting that there is no linear relationship and concluding that there is, and a linear model is appropriate. Boom, that's the final slam dunk, done with the problem, p-value, statistical evidence, finished. Okay, so that's what this does for us. Which, by the way, I can't remember, when I said I covered this up right here, see all this data about the y-intercept, I covered that up because it's extrapolation anyways. We don't make any estimates or predictions about the y-intercept. So that's why we don't ever want this information. I did have some people in earlier classes ask me, well, why does that even come out on the computer printout? Well, maybe you're in an industry that the y-intercept is not extrapolation. Maybe your y-intercept is in the spread of your data. Then that would be of interest to you, that y-intercept. Okay, but let's do a couple of other things, and then I'm going to get you going on your assignment. First, R squared adjusted is just extra information. You don't use that. It has to do with taking out the high, taking out the low, and getting a smaller variability here. But look, this R squared is 35.8. What does R squared tell you about the problem? Not the linearity. Okay. R squared is the coefficient of determination. Oh, Ernie missed this on Friday. Should we sing for him? Okay. Yes? Only if y'all do that too. Everybody gonna do this? Okay, you ready? Here we go. Coefficient of determination. The percent of variation that is found in the y. Coefficient of determination. The percent of variation that is found in the y. It can be explained by the changes in the x, or it can be explained by the model itself. Oh, coefficient of determination, the percent of variation that is found in the y. You didn't want me to do my fancy?
Your big ending.
Oh, he had to be here on Friday for that. Yeah, you missed the big ending. Okay, so you will be asked to give a verbal description of what this is saying, and that's 35.8% of the variation in volume can be explained by the changes in height. All right, final thing, which I'm not going to talk to you about in depth today, but you do have to identify it in your assignment just to get used to seeing what this is. This here, 13.4, this plane S, is stated right here. It represents the standard deviation of the residuals. Standard deviation of the residuals. We will go into depth on that tomorrow, but essentially, here's what's happening. I'm just going to give you a quick version. If this is your residual plot, and this is your prediction line, and you got all of this data here, well, guess what? That's one standard deviation up, and that's one standard deviation down, which in this case is 13.4. So that's 13.4 above predicted. And this is 13.4 below predicted. Well, what's two standard deviations out going to look like? Yep, 16.8 above predicted.
26.
Oh, dang.
26.
Sorry, my bad.
That was my bad.
26.8 below predicted. Well, guess what happens, people? 68% of all of the observations are found in this section here. 68% of all of the actual points are within one of those standard deviations away from predicted. And then what happens here? We start getting less, but it makes a total of how much between two standard deviations out? How much? This is going to, how much percent of all the actual values? 95% of all the actual data are within two standard deviations of the predicted. We'll get more into that tomorrow, but I want you to just make sure that you can identify that this is the standard deviation or the standard error of the residuals. Now, your assignment for today that you're going to do during class while I'm telling you your test grades is to complete numbers 1 through 4 in this notes packet, actually. Okay? And stop at number 5 because I want to go over and remind you of how to do this number 5. It's got something different that we've done before, but we haven't seen it in a while. One last item. On this number 4, you will be asked to find the mean of x and the standard deviation of x, the mean of y and the standard deviation of y. Where do you let your calculator find all those extra things, extra statistics about your list? You're going to want to go to one variable stats and calculate for the appropriate list, because then that gives you all the information you want about the list of data. So there's my little hint to you on that. All right, let's go to your assignment 1 through 4. When you're done with that, you're done. I'll be giving you your things. Tomorrow we'll go over this and your 1 through 10 that you had on the weekend.
So you have to have it.
Yeah, I don't know. I might. If I get